Welcome to lectures 11. We're in the second to the last lecture of this course. Yay! Everyone seems excited. Okay, so today we're going to talk about concurrency control. Oh my god! We have new terms here. Concurrency. What the is it? Okay. So, before we get into it, so I just finalized the guest lecture. So we could be that she gave you like a feedback on hackathon last semester, right? She's gonna give us like a guest lectures on March the 4th. Her research is mainly about social network analytics, so which is kind of like related to data, working on massive data. So she's gonna give us some things. In case if you are free on March 9th, which is in the morning, I am also teaching the big data course for your senior student, second year and the third years. I also invite another guest lecturer as well. That guest lecturers, he will give a talk on March the 9th, which is on Monday morning. So in case you are free, if you want to join, feel free to join, okay? The class will be on the 7th floor. Okay, so that's about guest lectures. I'm still not sure about her topics, but she said she's going to talk about something about Instagram or like that. Okay, the next one is about projects. So, no class on next Tuesday. Yay! At least I see someone excited on it. Okay, but the reason why we don't have a class is not about it is a holiday, so on and so forth. It is because we have a project halfway check-in, and I want to give that time, 2 hours, for you to discuss the project with your project advisors, right? So I post the instructions on the forum already, right? You should do it before February 24. Actually, like within February 24. You should do the halfway check-in. The halfway check-in means you need to deliver the list of features of your application and the ER diagrams. Personally, the halfway check-in should not be your first time meeting with your advisors. You at least need to meet before that time. For me, this week, you make an appointment. This week, maybe list of features first. This should be very easy when you can make it within an hour or less than an hour, right? And then discuss with the advisors, see whether it makes sense or not. You may want to draft an diagram as well. So the halfway check-in, we're gonna give you 10 out of 100 from 10% of the project grade, which is 2.5% of the total grades. We expect to see a good list of features in your diagrams, but I think you can meet with advisors as much as you want. So please do it like in the iterative fashions. You know, you get the first draft done. You would go discuss with your advisor to get a feedback, and then you incrementally improve, right? What you have, get the feedback. Improve, get the feedback. It is good. They are good, right? So start early, don't wait for it. That is why we have 4 weeks. We don't have only one day, right? We have 4 weeks. So spend some time on doing it, on working on it. Solo project. SP4, I'm so sorry. At first I thought I could get it within today, but unfortunately no. But I would say that it will be out tomorrow. Hopefully. If not, then I'm gonna remove SP4 and give you free grades. But I think it could be done. Okay. By the way, SP3 was due yesterday. In case if you don't know, all you have 3 grace days, which means you can submit 3 day late without having any penalties for only SP, in case you don't know. And you can only use grade A is on SP, which means either this SP3 or SP4. These are like only the left one. So just use it. You just have like 3 grade A's, just use it. But if you run out of your if you run out of the grade A's, then you need to, now you're gonna need to resubmit, you need to submit late with penalties. 1 day equal to 25% of your SP scores. So I don't think you want to do it. Okay. Just to preview in case I can get it done, because I'm writing it. So the goal of SP4 is like an overview, it's like an overall of this course. I want you to build the actual database management system, but in a very smaller versions. So you want a simple in-process key value database management system. In-process means like DB that you can just import DB and then use the database. That means in process. Key values mean that the interface will be only, the data model is just key values. You have a key, if you want to retrieve data, you retrieve data using the key. You can put data in using the key and the values. Check out the data model lectures. We have discussed about the key values data models, right? So if you know the key values data model, you're going to see that it's a very simple one. You don't need to have a very fancy SQL queries. You only need to have get and set. That's it. So in this project, there will be 3 parts: storage, snapshot, query interface. The first one, storage. You're going to build a storage of the DBMS, and the storage is a hash table that I talked about it before in the query acceleration lecture, the last lecture. Right? It will be a simple hash table, so don't need to be worried about it, I guess. This one, something that we haven't discussed about, we haven't talked about explicitly, but we definitely can do it. We call it a snapshot. What is snapshot? Snapshot is when you want to save the current state of your database. Like a backup of your database. Which means you save, you kind of create a file containing the entire state of the database, including all the data. And you take a snapshot. It's like when you take a screenshot. Which means when you take a screenshot, you're going to get the current state of your screen, right? But this one is you take a snapshot. You get the current state of your database. When you get a snapshot, let's say whenever you want to rewind and get back to that state, you should be able to load your database from that snapshot, put it back, so you can now revert back into the state that you want. In the world right now, many applications that do snapshot frequently in order to do the backup. That is why I think it is good for you. It's a good time for you to try implementing this. I can tell you that it is easier than you thought. And saw many people in SP1 use Pico libraries, right? Pico basically use one of the use cases of the use cases of Pico is to do this. You can do this perhaps within 1 or 2 lines of code. So it is easier than you thought. Okay. The last one, query interface. This seems cryptic, right? But basically just needs to create CLI. That's it. In which we have done it since last semester. So it's not that hard, it's very easy. So I believe that the hardest one would be to create a hash table, in which I don't think that it is hard. Okay. Final exam, we talk about it a lot. Final 3-hour written exam, fully open book according to the university policies, which means you can bring in anything that your university is allowed. If the university doesn't allow, then you are not able to bring it in, right? So most of the thing would be electronic devices that you cannot bring in. Waters, food, I don't think they allow, but talk with some stuff, right? They know better than me. Okay? Yeah, bring it in, just print. Honestly, I don't want you to print out a lot. I want you to use a lot of papers. Save the earth and save the world. You know, I know that many of you have an imagination of printing all the slides and bring it into the exam rooms. I know that many of you want to do that. You're definitely gonna do that. If you want to do that, at least, you know, when you want to print it, there will be an option that you can do 8 slides per page. Hit that button. Okay, so you save the word by 8 times. Also, do like 2 sides. You know, print using 2 sides. Now you save the word by 16 times. Doing that. Okay. But my personal preference is whenever you encounter so many books exams, slides mostly when you bring it in, it doesn't matter that much. It's better that you understand the slide first before getting to the exam. Okay? So my personal suggestion would be that you write some cheat sheets, scratch notes, summarize everything that you understand, and put it in to the sheet, to like scratch note that you want to put that you want to bring it into the exam rooms, right? Or maybe memo, put something that you think that you're gonna forget for sure. Okay. The practice exam has been posted on forums. I can say that it is very close to the real final exam. This is another of my imaginations. I believe that there might be some of you, this is only my belief. Put the practice final exam into Gemini, generate the answers, print out the answer from Gemini along with the practice exam, and bring it into the exam room. I think it could be one other thing that some of you may think of doing it. I am not restrict you from doing that. But I can say 5 minutes. Not gonna help that much. It may help if you are very fortunate that Gemini just put something useful for you, but I don't think so personally. So for me, if the way you should work on practice exam is you do it by yourself. If you want to know whether it is correct or not, bring it to me, send it to me through the email or something like that, okay? I will help you, okay? Give you feedback. But basically, if you're gonna send me an email, do it early, okay? You should not do it the night before the exam. Right? I will also give out previous exams as well. But just to know, a huge note that some questions may be out of the scope for this class because I change the scope quite often. And so this is my 3rd time teaching this course. The first time, I only taught like SQL and ER. Perhaps that's it. The second time I taught a lot of things. Too many things. So that's why the 3rd time is more like the fusion between the first and the second times, right? So there will be some things in the first time that I put it in, something the second time that I put it in, but not often. Okay. So this one I have wrote down for you one day, right? So these are all. So there will be 13 questions in the final exam. You're not going to see the 13 questions because it is a secret question. But it's not secret anymore because I have told you before what it is. Okay, so these are the 12 questions. And these are the topics we're going to cover on. And for each questions, you could expect some of them to have sub-questions. For example, first question is about air resistance. We're going to see 2 sub-questions. The total score is 10. Right? So when you sum up all this score, you'll get 180, right? 180. Why do I why the sum is 180, it is coincident or something. So if you do select, right, some score from this table, you're gonna get 180, right? The reason why I want the total score to be 180 is because your exam you have like 180 minutes to do it. The scores here is for you to use it to, to expect the time you should spend for each questions. For example, the first questions, if you spend the time more than 10 minutes, means you are now lagging behind. Right? So use the scores to see whether you are lacking or you are running ahead of the times. Okay? And the one that has the highest score is the large community design within 30. So I give you 30 minutes on it. Only 2 sub-questions. And I can tell you right away that that 2 sub-questions is on the practice exam. Just need to bring on the right one. So if you look at the ER question in the practice exam, there are 4 sub-questions. 2 of them will be in the final exam. I don't think it's hard to guess. I don't think it's hard to guess. Right. The easy one that you should get for me, the first questions. The easy one would be the first one. This one. Oh, why there are only 3? I'm sorry. Yeah, I just moved it there. The easy one means if you know how to do it, then it's very easy. But the first one is easy, but you just need to do some reasoning. Okay, let me tell you the hard one instead, because I cannot see a lot of easy one. It is not that hard, but some of them are hard. For me, the hard one would be question 2. Yeah, 12, 10. Perhaps 4. These are the hard one. ER, if you are not familiar with ER, you perhaps so for me, I don't think the ER one would be the hard one, but I normally love to after I wrote my exam, right? I love to put my exam onto Gemini and let Gemini grade my exam. Gemini say that this one is the hardest one. I don't know why. But for me, it's not that hard. But in case if you trust Gemini, then you should be aware that this one is hard. So, the reason why I think it is hard for you is because it's neat. You cannot just open up slides and enter it. You need to understand enough that you can make a reason on it. But perhaps it could be very easy if you understand it well. Some FAQ from myself. Will there be SQL in the final exam? Yes, but mostly simple one. Some single table queries, DDL, DML, and unique constraints. That's it. You don't need to know join. This might not be 100% accurate. I cannot say that there could be multiple queries. There could be multiple tables query as well, but not with join. So you think about it by yourself, that which way do I gonna pose the multiple table queries without join? There is one way to do it. Maybe a few ways, one way. But there will also be multiple table queries as well. Only one of them will be multiple table queries. Alright, so the 30-minute pause and then just get into the lectures. And the lecture is quite long. So we have a short lectures for like 2 weeks already. This one definitely is going to be long. So be prepared, okay? Oh, we're also going to have a quiz today as well. Since we didn't have quiz for a while, so we're going to have a lecture quiz today as well, okay? So today we're going to talk about the first topic is about concurrent execution. I think that you know what is execution, but how about concurrent? Right? So the database management system like DBP, the other PostgreSQL, Microsoft SQL Server, Oracle database, that typically allows for multiple users to use the database at the same time. Means it could be two users, okay, trying to query your database management system at the same time. So my first question is, okay, let's say given these situations, which one should that DB process first? Okay, before I get to this question, does it matter which one should go first? Let's say if the user one queries go first, and the users two queries go after that, what would happen? What would be the difference? Okay, so user one gonna get all the students from the table, right? Cool. They could get like 10 students. User 2 insert others into the students. Which means, let's say, if user 2 get to take turn first, insert the Alice to the students, and user 1 query from it, actually user 1 not gonna get only 10 students. I'm just trying to think about the pronouns to describe this. Let's call it this. So this will get, instead of 10 students, this will get 11 students. So it matters which one go first, right? Because the result is different. But logically, perhaps it doesn't matter that much. Because as user 1 trying to query, this would expect this would have an expectation that database can be changed, because this database management system allows for multiple users. But in some cases, this should not be allowed, in which we're going to describe it in this lecture. So yeah, there are 2 possible results, right? We call a sequence of queries. We call it schedules. We have queries that can be arranged in multiple ways. If you have 2 queries, then basically you can arrange these as into 2 possible schedules. The first one, you select first and you insert. The second one, you insert first and you select. Results are different. When we have, okay, so this is the word schedules. Okay, this is the first terminology, schedules. The next terminology is transactions. This is also another very important term in database management system. Okay, transaction basically means some railway actions, which is a sequence of queries. But I have some asterisk sign here, because it's not always going to be a sequence of queries. It could be a sequence of something that we call read-write instructions. So some queries, not all the queries, except the definition queries, we tend to do 2 things: read and write. You do select because you want to read something from database, right? You do insert, you do update, you do delete. means tend to write something onto databases. A transaction is basically a sequence. A transaction is basically a sequence of queries representing a single action. For example, if you want to send money, not you, if you want to use an application that can send money from your account to another account, one of the ways is the application should be implemented in a sequence of, for that action, could be implemented as a sequence of 3 actions, 3 queries. The first one is you check your balance first. Whether it is sufficient for you to attempt to do the money transfer. The second one, if, so you have if here. If the money is greater than or equal to 100, then you attempt to do the next step, which is you update your balance by incremented by 100. Okay, and lastly, you need to increment the target balance, right? Destination, whatever you want to say. By 100, right? So this could be a sequence of 3 queries for doing money transfer. Use 3 SQL to do it, along with some if statements, right? Looks like there won't be any problems, right? But you know, your mobile banking applications, how many users use it? Let's say in 1 minute. Given in the world of mobile banking, how many transactions do you think have been made? A lot. So imagine that at the same time, if your database management allows for concurrent transactions, concurrent means you run the transaction at the same time, or I'm not sure about the spelling, but yeah, something like that. Or simultaneously, right? That is concurrent. Concurrent transaction means you're running multiple transactions at the same time. For example, this database management system, you allow for user 1 to send 100 to user 2. User 2 allows also send 50 to user 3, and this database management system tends to process it at the same time. There are some, okay, even though I say that there is allowed it, but some of them may not allow it. For example, Redis. Redis is also one of the database management that I have talked about before in the data caching lectures. This is one of the systems that do not support concurrencies. So if you see the system that do not support concurrency, then you're not going to have this problem in these lectures. So the point is that now you know the word transactions, right? You also know the word concurrency. You also know the word schedules. Given that you have multiple transactions, now you're going to have tons of schedules. Yeah, you have transaction A, right? In which transaction A consists of 3 queries. Transaction B consists of another. Let's say you have another transactions. Transaction 1, you want to transfer from account 1 to account 2 by 100, right? With amount 100. Transaction B, you also want to transfer from account 1 to account 3 by 50. So now you have 2 transactions. The number of transactions You can, the number of schedules, given these two transactions, is 20. You can create 20 possible schedules from doing this by shuffling. You do B1 first, A1, B2, A2. You can just shuffle it in 20 different ways. Okay, so there are multiple ways to do it, which gonna give you different results. Some that could give different results. But given the money transfer like this, should it have multiple results? Shouldn't, right? If A transfer from account 1 to 2, 100, right? With 100 and with the amount of 100, and if another one, with account 1 transfer to account 3 with the amount of 50, then you should expect that account 1, the balance of the account 1 should be decremented by 150. And account 2 should get more, 100 more, account 3 should get 50 more. This should be the only result that you should get. But given multiple schedules, you will see that some schedules that do not go, do not allow you to get those results. Let's see. But this depends on the balance as well. So let's say we have balance one side with 100 and balance 2 is 0. So this is one of the schedules that we do all the transaction A first and the transaction B next. By the way, when you arrange a schedule, you cannot just switch do B2 first before B1 because that is not logically equivalent. Because it is transactions, it is a sequence that you need to go step by step. You cannot just do step 2 first before step 1. Okay. For schedule ones, let's start with the first one. Okay, we just need to read the balance, right? Because we want to check whether the balance is sufficient or not, right? Move on. Let's do the transition. Let's do the next queries for the transition 1. Okay, now we deduct the balance of 1 with 100. So now the balance is 0, right? Then we add the balance of 2 by 100. Looks good, right? Looks good. Then now we check the balance. We're gonna do one other transaction, right? We're gonna check the balance of account 1 again. 0. Alright. And if you remember the pseudocode, we also check whether the balance is sufficient first, right? Before we attempt to deduct. And given this balance that we select, we got zeros. Zeros definitely lower than 50 that we want to transfer. So the transaction should stop here. Should not be proceed, because if you proceed, then you're gonna get negative something. The balance is good. It should not be that, right? So remember this, right? We check this as well. Actually, it should be 50 for this one. It should depend on this amount, right? Let's consider another schedule. Now, this schedule has something to limit, right? That, okay, can I just do select balance for B, the transaction B here? So we do it a little bit early, but you know, the sequence the sequence of the transactions are still reserved, right? You still do A1, A2, A3 in order, B1, B2, B3 in order. So you just interleave B1 between A. So let's do it. Okay, so we select balance, we got 100, it's cool, wonderful. Now we do this, we select the balance, we got 100, wonderful. Right? So basically, this one, we now pass through the if statements because the balance that we have is greater than the amount that we require to transfers, right? Then, okay, let's do update. Okay, looks good, still looks good, right? So okay, we deduct by 100. So okay, balance 1 is zeros, right? Then we add balance 2 with 100. Looks good. And here's the thing, because given this, we pass through the if statements, which means this one can be executed. And if it gets executed, oh no! Now the balance is negative 50. Should it be allowed? No, you don't want that to happen. And this is a problem when your database manager is allowed. for concurrent transactions. How to solve it? The first solution is don't use database and allow for that. Okay, have you wondered why do we need concurrent transactions? Don't just be like block all the concurrent transactions. Just do that process one transaction one. That's gonna solve all these problems, right? We're not gonna have this kind of problem, this kind of change. Why? Why do we need to have concurrent transactions? Why? It's not that we need to. Why should we have it? Okay. So this will be the agenda. Today we're going to talk about transactions and concurrency control protocols. This one, technically hard. It's hard. This one, perhaps doable. Okay. So transactions. Formally. So previously I told you some definition of transaction, but in a very informal way. But let's get real. Transaction formally. Okay, first, before you're gonna know the transaction, the formal definition of transactions. The formal definition of database before you get into this transaction is that it is a fixed set of named data objects. So it's basically a set of data objects that has name, that have name. For example, you have object X, which could be a row in a table. You have object Y, which could be a field, one value in a table, in a row. You could have object C that could be the entire table. You could have object A that is a whole database. So when we talk about the word data object, basically it can be anything in the database. It could be a row, a field in a row, an entire tables, a group of tables. It could be multiple rows as well. Right? So that are data objects. A transaction is formally a sequence of read and write operations made upon data objects. So there are two operations, right? Well, let's use the word instructions. There are two types of instructions. The first one is OR. OR here means read. If you do OR X here, which means that we would like to read data object X. You're not going to care whether what's going to be the type of the object. Right? It could be tables, it could be rows, but let's just say X. It could be anything. We want to read X. And WX. You can guess. If I is read, W will be write. Right? Transactions will start when you use command called begin. In some database management system, you may see command begin transaction. When you declare, when you run begins, then now database management system, you see it as the start of a new transaction. And if you want to stop the transactions, if you want to complete the transactions, you're going to use the command commit. Commit means this transaction is successful or complete. It is the end of the transactions. Well, in this class, I may abbreviate the word transaction as TX. Okay? TX means transactions. Commit is the end of the transactions. But there could be a situation that the transaction somehow get into some errors or get into some weird situations, and we don't want to proceed. And not only that we don't want to proceed, we also want to revert everything that we did for the transactions. If you want to do that, you can do rollback. Rollback do two things: stop the transaction and revert all the effects since the beginning of the transaction, the beginning of the transactions. So, begin, commit, rollback. People will taught you, right? Okay, in the last lab that we have. So you're gonna see it better, the transactions. But today we're gonna get into the theory view of transactions. Okay? Any questions, comments, concerns before we move on? So this is gonna be something that you should expect when you write a code. You begin, right? Begin means you start transactions, right? You select balance, right? You update account and you update another account. You commit. If you don't commit, all of these actions will not reflect on your database. In case that you start begin, okay? So when you do insert or update before, right? Before this class lectures, we haven't done any begins transactions. So that's why when you run into the effect process already. But now if you do begins, all this effect won't reflect on your database until you put commits on it. So the reason why many data, this will be for all database management systems, or most of them. The reason why you're not going to see the effects of these updates is because database management systems would like to maintain something that we call atomic setting, in which I'm going to teach you in the next lecture. Atomic setting means a transaction cannot be divided. In other words, transaction must be all done, or none of them done. None of the instruction done, or all the instruction must be done. This is to make sure that the transaction won't be halfway complete, which could cause something weird, right? Bad, right? Database management system tends to has these characteristics, these properties called atomic cities. And let's say now you run transaction A, sorry, transaction B, and then you run transaction B. When you encounter this, we got into if, right? If balance less than or is greater than or equal to, in which it should not be. Therefore, you should not proceed. Should stop and revert all the effects. Fortunately, this is just read-only query, so it doesn't put update anything. We do not update the database. So basically, we don't need to do any revert, right? But we just do rollbacks, to stop the transactions. Okay. Any questions, comments, concerns? You will see this better in the lab. Okay. So what I'm going to say is that whenever you want to create an action in the data for that has an action has a sequence of queries, you just put transaction on it. Begin and commits. Begins before and commit after. And if let's say you have some conditions that you need to roll back in, for example, the balance checking, right? You can do like if when you go into if, right, you do the update, and you may want to do else, and then you do roll back here. Okay. Roll back stops the transaction and revert all efforts. I got the animation wrong on next slide, so you're gonna see the arrow here. Okay. So, in theory, if we're gonna view transaction as a sequence of queries, it will be too much information. That is why we tend to represent transactions as a sequence of read and write instructions. Instead of this, we're going to simplify it into this. So for select, it's simple. Read the balance, right? I'm going to say read balance one. But for update, when you do update, normally, especially if you want to do balance equal to balance subtracted by 10, 100, means you need to read the old balance first. So actually, in the database management system, when you do this, you read balance first. This update breaks down into multiple substeps. You read the old balance, you subtract the old balance by 100, and you write the balance with the new one. The reason why I kind of like made the assignment, the subtractions here in a lighter color is because for transaction we only care about read and write. So for this transaction, basically we do 2 read and 2, we do 1, 2, 3 reads and 2 writes. Okay. So transaction A and B could be something like this. It could be something like this. Actually it should be balance 3. But yeah, let's assume that it's balance 2. Okay. Right? So this is now transactions in a very theoretical way. Okay. Any questions, comment, concerns? You're still with me, right? Okay. So one of the way to not get into trouble with concurrency issues, the weird results thing is we can do something that we call serial execution. Serial execution means you do one transaction entirely. You need to complete all the steps first before you get to move on to the next steps. By doing this, basically you don't do any concurrent transactions. You just do the chicken shell things, you just run transactions sequentially. Doesn't give you anything, right? Definitely they must not have any conflicts. So with the weird situations, I'm gonna say that when we encounter my phone doesn't like me. Hello? Okay. Oh, we're back. So, when we encounter the weird situations, we call them conflicts, right? You're going to see the word conflicts clearly in the next few slides, okay? But one of the ways to build a schedule of 2 transactions without any conflicts is to just have no interleave. Just not interleave instructions. Just completely do transaction first transaction and then continue doing the next one. But again, I have told you this, right? I have asked you once that, okay, if you do this, then you're not going to have any issue. Why? So why do we need to deal with the concurrent transactions? Why do you want to do it? The reason is about this. Serial execution has a problem, which is very critical. Let's assume that you have n transactions. And perhaps it is one transaction that spends like 1 day to complete, which is possible. For example, in large company, there could be a transaction that trying to make a report for the entire company. Then they need to query data from other table, do a lot of joins, and do a lot of aggregations. It is possible. And that transactions If you say that you're going to do serial execution, means, let's say, on that day, we have other small transactions that could be done within a millisecond. They need to wait until this big transaction is done. If you is Uber, right? Let's say Uber need to create a report. They put on one transaction, using maybe one day is too much, maybe 5 hours. Then someone, hey, I want to order food. I order food. Oh, I need to wait for 5 hours first before I can start ordering the food. You don't want that. No one wants that. And that is the reason why serial execution doesn't work in real life, especially if you encounter this kind of problems. But if you don't encounter long-lived transactions, perhaps serial execution is one of the good ways to go with, right? So there are pros and cons here. So it's better that you have some degree of concurrency, allowing for small transactions to interleave the big transactions. Okay, the overall time to complete the same, but now whenever you get small transactions, they can be completed at the moment. So they don't need to wait. Wouldn't it be better? Now your system is more responsive. My question is, how to allow for concurrencies while making the same results as serial executions? So the point is that serial execution should be the one that you want, right? Because it has no conflict. Even though there could be two possible scenarios here. Transaction B could go first. That still count as serials, right? That still count as serial execution. So what I want to say is that what you want is what you should expect is that we should expect the serial execution results, the results if we run transactions sequentially. But we allow for some interleavings. How to do it? So before we get into it, I would like to describe the conflicts much better, okay? So the conflict is a situation between two instructions. Two instruction conflict if and only if there exist some items accessed by both instructions. There is an item, data objects that accessed by both instructions, and at least one of these instructions want the items. That is when the conflicts happen. For example, you have data object X, transaction 1, I'm going to call it T1, T2, T1 want to read X, and T2 want to read X. This conflict happens because, let's say T2 write first, T1 will read the updated one. But if T1 read first, then T1 gonna read the old one. So if this get interleaved and can be shuffled, then now have multiple possible results. Given this, now we have three types, and we simply have two types of instructions, right? Read and write. Forget about begin, rollback, commits. We have two types of instructions, and the conflict is that when we have at least one right. So we can have three types of conflicts. The first type is what we call dirty read. There is basically someone write first and then another one read. The next one is loss update. Loss update is some transaction write the data objects, and another transaction also write onto the same data objects. Unrepeatable read is you read first, some transaction read it, and someone write on top of it. For me, at first, I thought that when I learned this, I thought that this write and read conflict, write conflict, read and write conflict, are a lot easier to interpret. Somehow, after a while, I found that actually the first term here, dirty read, loss update, unrepeatable read, are much more meaningful. So we're gonna see. First, let's talk about write-read conflict or delivery. Write-read conflicts happen when a transaction reads an uncommitted values from other transactions. You do one transaction, you write first, and then the next transaction you read. Dirty read means you read uncommitted values. Uncommitted values mean the value get updated in A, right? X get updated in A. So now, okay, so let's say transaction A, X, the value of X star at X0. First transaction A read X, okay, nothing's happened. Then transaction A update X into X1. Let's say now transaction B trying to read X, but you haven't commit or roll back transaction A. Which means, actually this should not be the one you read, you read, right? Because the transaction hasn't ended. Let's say the transaction somehow get into an error and need to roll back. Then this transaction can read some dirty values. Some value that isn't real at the moment. And this is the case, that case, right? You read, transaction B, you read X1, and transaction A say, okay, I need to stop because something wrong happened, roll back, and then go back to X0. Transaction B now read something that doesn't make sense. It's not real. This shouldn't be happening, right? This shouldn't happen. That is why we call dirty read. We read data that is not committed. Forget about it. Ignore me. Okay, so this is dirty read. Okay. I think something is walking. Okay, let's see some real world scenarios. So let's say that there are two transactions. A wanted to deduct money X by 50. Could be money transfer, right? B would like to assign the value of X to Y. So it like to copy X to Y in order to make a report. Okay. There are two transactions doing at the same time. Right? Transaction A. Okay, first we read X into A and put to A. Right? Then you write X equal to A minus 50, which means you want to deduct X by 50, right? So now X is 50. Okay, cool, wonderful. Then transaction B, hey, I wanted to read X again because I wanted to copy, make a report, right, of the current balance. So I read X and put it to B, and then write down Y equal to B. So now Y is 50. X and Y 50 looks good, right? Because now we accomplish the deductions and we also accomplish the copy. But somehow, it may get into some problems. We need to roll back. So no, roll back. So roll back means we're gonna rework this, okay? Instead of, so this one we deduct 50, so we need to increment it back into 100. Okay, now, cool. Okay, we roll it back. And transition to B zero. Okay, we done creating a report, so we're gonna commit it. Somehow, this is not true, right? Because if Y should be equal to X, but X is 100, it's not true, right? We create a faulty report. So this is the dirty read. Understood? Dirty read. I haven't told you anything. At first I tried to remember the word right read, but well, I mean, understanding the word dirty reads is a lot easier, you know. It's a lot meaningful. Because you're also going to see the problem, the actual problems. Next, write conflicts, right? Or loss update. So write conflict is basically you overwrite the uncommitted values overridden by other transactions. So one transaction is trying to write value. So write X1. Okay? And then another transaction just overwrite this. You get X2. So with X here that you just write in transaction 1 get wiped out almost immediately. Right? So you're not going to have a time to use X1 here. So let's see some real world scenarios to give you a better view on the loss update, right? So let's say two transactions want to do the same thing. They want to deduct x by 50. Okay, so the first transaction, okay, we're gonna read x. Then, okay, we move on to transaction B. We allow B to do some instruction. Now B, read x as well. Then, okay, A, okay, let's deduct x by 50. Let's deduct what we read by 50 and write it on x so when we get 50. B said that, hey, I wanted to deduct x as well, but this is what I read before. I know that x is 100, so we're gonna deduct x by 50, and we're gonna get 50. Does it make sense? We do through a transaction that deduct x by 50, so it should be deducted by 100. But given that we lost this update, we lose this update. That is a reason why, even though both of them commit, we still get 50, which is not 0. We lose the update here. That is why we call it a loss update problems. Loss update conflict. Okay? Any questions? The next one, the last one, read-write conflict. This one is kind of, could be a little bit hard to understand. Read-write conflict or unrepeatable read, right? A transaction reads the same object twice but receives different value without it modifying the object by itself. This situation doesn't happen in serious execution. Let's say you do this transaction A and transaction B sequentially, then this situation wouldn't happen. Okay, so let's see. So even though I say read-write conflict, so it's actually the conflict between write and read here, but the effect will happen when you do read twice. Okay, in transaction B, if we do serial execution, if you do to read without doing any modification, you should get the same values, right? But now we allow for interleaving. So, transaction A, do the write to x, updating x from x0 to x1. Now, transaction B, when we read it, the first time we get x0s, but when we read it the second time, now we get x1 without it modifying this. So if this is bad, how bad it is? Let's see. There are some real world situations. So let's say if transaction A deducts x by 50, and transaction B tries deducting x by 80 if x is greater than 80. So we have some conditions, right? Okay, so first, transaction A, we read x. We get 100. Okay, cool, wonderful. Next. Then transaction B, we read x. So this is the first time reading x, right? We get 100. Cool, wonderful. Now transaction A deduct x by 50. And then assign, write it down to x. So now x is 50. Then transaction B, okay, we check whether it is greater than 80 or not. Yeah, it's greater than 80, so we're gonna proceed. Let's say if we do another read here, sometime we get 50. Which is not the same as 100. But since the first read, we got 100, it can pass through this if statement. Then, okay, when we want to read it, now we get 50 and we update by 80 and we get negative 30. So, the number of deduction makes sense, but somehow the unrepeatable read get us past through the unrepeatable read conflicts, get us past through this point, the if statements here. So that is why we get the problems, right? Because we read the two times that we read in transaction B, between them we didn't do any modifications with the data with the value change. So there are three conflicts here. Right? Write, read, write, read, write, 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 read, right? The first one is dirty read. The second one is loss of date. The third one is unrepeatable reads. So these are three conflicts. There's a special case as well. We call it phantom reads. Phantom reads happens in this kind of situations. So you kind of like would like to select something from a table, and another translator insert this. Somehow this is pretty similar to unreadable read, that the first read and the second reads are not the same. But this doesn't happen with the data object that much. These are the different data objects, right? This, we're talking about X, that is a table. This, even though we also write on X, but basically just put new things into X, right? So this is pretty similar to unreadable read, that we can run the same query at the same time and we get different results without modifying it by itself, by the translator itself. Okay? So these are other conflicts. If we can remove all of the conflicts, if we can ensure that the schedule doesn't have these conflicts, we should get the same result as serial executions. How? So before we get into how, let's have a break first. Let's have 10-minute break and get back together at 10:35. Right? 10:35. Okay, I'm gonna put the pause on it. Okay. Right, so now you learn all the conflicts. And I told you that if you can ensure that your schedules, even though interleave, doesn't have those conflicts, then you're good. Now you're good to go. You should get the result as same as the serial executions. Right? So, okay. So the goal is you want interleave schedule without conflicts. So there is some theory saying that if, let's say, you have two schedules, schedule S and schedule S prime here, if you can swap non-conflicting instructions in S and make it equivalent, the same as S prime, then S and S prime are what we call conflict equivalent. So this is the first theorem, okay? And then a schedules is conflict serializable. So that is the second term here, called serializable. Conflict serializable. So that's what it means. It's not a serial execution, but it gives the same result as your execution. That is a definition of a serializable. Serializable means that it could have interleave instructions, but the result is guaranteed to be the same as serial execution, which is what we want. So we want the schedule to be serializable. One other way to make it serializable is we can make it into something that we call conflict serializable. Conflict serializable happens when the schedule is conflict equivalent to a serial schedule. Which means if a schedule is going to be conflict serializable, if it can swap non-conflicting instructions to make it serials. If you can do that, then the schedule is conflict serializable, which means the result will be the same as your execution, which is what we want. This is to check whether the schedule is conflict serializable or not. Okay? So to check if we just need to swap conflicting instruction. Let's see. So, given these two transactions, what are the conflict instructions? So now you also need to see the data objects here, that the first 4 times here, we read and write onto X. Then this one we read and write onto Y, right? So let me ask you whether this and this are conflicting? No, they're definitely not conflicting because they are working on different objects, which means we could swap it. could swap it. So we swap it. Room is serials, which means this schedule is conflict serializable. Okay? The result will be equivalent to the serial execution of these two transactions, while allowing for concurrencies. I mean, right now I'm asking you to trust the definitions, trust the theory, okay? So we don't have much time to prove on it, but yeah. So basically, if we can swap non-conflicting instructions and make it serial, then it's safe. That is what I'm trying to say. Right. So then it's safe. How to ensure? So next one. Now we know what can be safe, what can be considered as a safe serials. Next, how database management system how the database management system enforce that all transactions must be executed in the safe schedules. That is what database management system should do. Because when transactions coming in at the same time, the schedule is going to be randomized. How do we do some things to make the schedules be conflict serializable? That is what database management system need to do. And that is something, the way to do it is the database management system the database management system need to follow some certain concurrency control protocols. Protocol means rules, set of rules. So they need to enforce some rules in order to ensure that all concurrent transactions are scheduled as conflict serializable. So, but before we get into that part, sometimes some database management system allows for making it more relaxing. If you want serializable by default, it will try to make all the schedules of transactions be serializable, which is what we want, right? But sometimes you may allow for some situation. For example, you may allow for repeatability, right? Or you may allow read committed means. So allow repeatable reads means that you are not ensure that we're not going to have unrepeatable reads, right? You could have unrepeatable reads. Sorry. Repeatable reads here means that the read must be repeatable, so you block all unrepeatable reads. But for the others, like early reads, like loss of data, occurs. Right? Read committed. Now you're not ensure repeatable reads anymore. But there will be something that ensure like committed records can be read, something like that. Right? I just want to say that not all DBMS need to ensure serializable. It depends. And there are also two types of serializable. The first type is what we just discussed, conflict serializable. There are also another level, which is what we call a view serializable. View serializable is quite very hard to understand, so that's why we dropped that topics. Okay? But this is basically trade-off between the consistency and degree of concurrencies. Right? If you want to have a lot of concurrencies, then you need to get to a lower acceleration level, so that you get less blocked by DBMS. You get more concurrencies, but the consistency of the data may be weird, you know. But if you get into serializable, then it's equivalent to serial execution, you know, the consistency, right? Even though it's gonna block you a lot, right? Make a lot of rules, make a lot of restrictions, make a lot of constraints to make this schedules serializable. Okay, so in order to implement those isolation levels, either serializable, repeatable reads, so on and so forth, there are at least 3 mechanisms to do it. The first one is blocking. The second one is to use timestamps. The third one is to have multiple versions of each item. So there are at least three mechanisms. That's some of the first way, the first approach. We call it lock-based protocols, or we use locking. Locking means we block others from working on a certain data object. Like we hold a lock that right now I'm working on this object. You cannot work on this, right? So that's basically a lock, right? In database management system, we typically have to pass at least two kinds of locks, locking two nodes. The first one is exclusive. Exclusive means, let's say this object is mine, right? Let's say if I hold the exclusive lock here, means that this object will exclusively be mine at the moment. You all cannot write or read on it. But there is also the next mode. In order to make more concurrencies, we call it a share mode. Share mode means, okay, I'm working on this item. But if you want to read it, I also allow you to read it as well, but you cannot write on it. Or basically, read-only mode. Read-only mode. Multiple people can read on it. But if so basically, when you do exclusive mode, means that only one person can write it. Because if multiple persons write it, troubles happen. But well, if you only read it, if all of you want to read it, it should be fine, right? So the data not going to be changed, right? So if you reflecting on this, many texts, but see this one. S here means share, X here means exclusive. Let's say if one transaction hold share lock using share mode. Other transactions can also lock this item as well, but using share mode. Share mode allows the transaction that hold a lock on the share mode should only do read, should not do write. If the transaction wants to do write, they should hold the exclusive lock. In which once they hold exclusive lock, now other transactions will get popped out, will get kicked out. And this forms something that we call one other protocol that we use lock as the main mechanism called two-phase locking, 2PL, two-phase locking protocol. Again, this is theory that I want you to trust on it. I haven't had time to prove it, okay? So two-phase locking say that it will ensure conflict serializable, which is what we want, by breaking down these shells to two phases. All the shells must have these two phases. The first phase is growing phase. Once we acquire lock, once we start locking, we can only do locking. We cannot release any lock. We cannot unlock any lock. Right? So when you plot a graph, you're going to see that we only lock. We're going to make it stricter. Could start with share and then upgrade to exclusive. Or you can lock other things as well. You can only do lock. We call this a growing phase. Once you release a lock, once you unlock some lock, now you need to unlock everything until you can start the next growing phase. Right. So, phase 1, transaction may obtain locks but may not release lock. In phase 2, transaction may release lock but may not obtain locks. Okay. How locks work, right? So you see, so I bring up one conflict schedules, right? So this one is not conflict serializable. You cannot just swap. So all these you cannot swap because they are conflict. They are like all of them. All of them are conflicts, right? Like this one. This is read right. This is write right. So it's conflict. You cannot swap. So definitely this is not conflict serializable. How locks? How 2PL helps? 2PL will do this. Whenever you want to read some things, you're going to hold the lock. Actually, it should be share lock, but let's say we want to be very strict. We hold X lock, we hold exclusive lock on X. If we hold exclusive lock, then even though we want to do this, we cannot do it. Because it gets blocked by this which means we need to wait until X get X, the locks on X gets unlocked. Then we can proceed to lock the X and start doing the things. 2PL is basically you hold a lock in order to block other transactions from working inappropriately. So this is what we call lock-based protocol. One of them is 2PL. 2PL is not a silver bullet. They also has a lot of issues as well, in which I haven't had time to cover it in this class. It's maybe too much as well, but it could be an issue called deadlock. Deadlock means this one also want to hold lock, this one want to hold the same lock, but somehow this one waiting for this one to unlock, this one also waiting for this one to unlock. So we get into something that a situation called deadlock, that these two transactions cannot progress because each other waits for the others to unlock the lock. Right? We need to they need to implement some preventions or detection mechanisms as well if you want to do like two-phase locking. So two-phase locking, it is a protocol that we call it is a pessimistic protocol. Means it assumes that most transactions are going to get into conflict. That is why we hold a lock. Then we ensure that all of them not going to be able to make any conflicts. But there is a trade-off as well, because if you hold a lock, then now let's say if you transact, let's say somehow the transactions are not getting into any conflicts. You spend some time holding the lock, unlocking the lock. Those are extra overheads causing time and space. So 2PL, if you encounter the situations that has ton of conflicts with you, because you think pessimistically that, hey, we're going to encounter a lot of conflicts, so we ensure by we lock it first. Next one is what we call a timestamp-based protocol. Timestamp-based protocol is the 2PL one, the lock-based protocol is being locked, right? Timestamp-based protocol is we assign timestamp for each transaction, the starting timestamp for each transaction, which will be unique. And we would use that timestamp to determine which one should go first and last, right? Which instruction, whether this instruction can be done or not. So one of the protocols that use timestamp is called TSO, Timestamp Ordering Protocol. Timestamp Ordering Protocol, for each data object, it needs to maintain two timestamp values. The first one is the write timestamp, which is the latest write. The timestamp that this one get latest modified. This data object get modified the latest. Right? Next one is the read timestamp, which is the timestamp that this data object get the latest and read. So what TSO or TSO do is impose rules on these read and write operations, right? It will ensure that any conflicting operations are executed in timestamp order. And out of all operations cause transaction rollback. It will ensure that read and write must be done in orders. If any out of order happens, the transaction will roll back. You will see. Let's say you read Q. You want to read Q, right? There will be two conditions here. When you want to read Q, you need to first check whether if newer transaction have written Q or not. If, let's say, new transaction write Q, means if you want to read it, you are reading uncommitted values, or you are doing dirty reads. Serializable should not allow dirty reads. So if you are entering that moment, you roll back yourself. Start doing it again. So when you roll back, now your timestamp of the transaction are larger. And now yours should be newer than the newer transactions. Then you try doing it again. This is the crux of the timestamp ordering protocol. You check the timestamp and you see whether you get the conflict or not. If you get the conflict, you go back. If you don't get conflict, you proceed to do it and you update the real timestamp of the data object. Okay? How about write? Write again. If newer transaction have read queue, so this is read. So when you want to check whether new transaction have read queue or not, you check whether the read timestamp of queue is greater than the timestamp of the transaction of the current transaction or not, that we are executing or not. If it is, then we encounter unrepeatable read, right? Because we want to wait. Newer transaction have read. If newer transaction have read queue, and now we are going to write it, then it's a read write which is unrepeatable read. If this transaction gonna read the queue again, right? It's gonna read different values. Then we encounter unrepeatable reads. Not the correct transaction. Other transactions may encounter unrepeatable read. That is why we go back ourselves and redo this again. But if you were also if newer transaction have written queue, write conflict is loss update. If loss update can happen, we should make it happen, right? We roll back ourselves and redo it again. So you're gonna see the crux that if we encounter conflicts, given the timestamp, then we check, we step back, do it again, we redo it again. Now I think you can guess the downside of this method, right? Otherwise, just proceed the update. You just update the right timestamp of the object. That's it. So, well, I think you can guess. It will be very good if you don't encounter a lot of conflicts, because you don't need to acquire log, you don't need to do certain things. But if you encounter a situation where conflicts happen a lot, okay, you're gonna see tons of transactions get rolled back, re-execute again and again. Not good, which is not good at all, right? So, yeah. So, timestamp ordering protocol is what we call an optimistic protocol. It thinks optimistically that conflict will be very rare. So, just need to try executing transaction first. Then if the conflict happens, we go back. Right? So this is the crux of timestamp ordering protocol. The third one, I'm not going to get into details much for this one. The key idea for this one is that if you do timestamp ordering and you are gonna do unrepeatable read, and you encounter unrepeatable read, you roll back, right? For this one, the idea of multi-version concurrency control is very simple. Whatever you want to write, you don't overwrite the old one. You create a copy and write on that copy. Which means now you maintain the old version and the new versions. Both old and new versions. Whenever you maintain both versions, let's say a transaction, at first it reads the old versions. Now it wants to do another read, but okay, other transactions may write on top of it. If you do multi-versions, now instead of you having only one copy, now you have two copies, the old one and the new one. If the transaction would like to read, the transaction that have read the object before want to read it again, just need to read the old one. They don't need to read the new one. Now, unrepeatable reads doesn't happen. Okay, let me draw a picture. So let's say you have queue, right? You have transaction 1, transaction 2, right? Transaction 2 read queue, transaction 1 write queue, transaction 2 read queue. So this is likely made unrepeatable read, right? So multi-version concurrency also say that, okay, first we read tx2, let's say q at first equal to 10. We got 10. Then we write maybe q to 20. If you do two-phase locking, if you do timestamp ordering, you change from 10 to 20. But if you do multi-version concurrency control, you maintain Q 110, and can you maintain the second version of Q 20. Now, this is 20. Then when you read Q here, you maintain 2 copies. So just need to read the first copy. That's it. We get 10 unrepeatable reads. Right? But you know, you're gonna have a lot of versions for each copy, which means you're likely gonna need a lot of storage for working on it. Right? But the good news is that normally if you do timestamp ordering, you need to roll back because you get another unrepeatable reads. But if you do this, you don't need to roll back. Or even if you do two-phase locking, if you encounter this, then basically you need to wait. You need to hold the lock here, right, before you want to read. But if you do this, no lock need to be held, no wait need to be done. You can just take the first version, that's it. So, in terms of speed, this is the protocol that gives you a lot of speed for reading. Right? For writing, okay, they are extra awaitings. That is the reason why this approach is the most popular one used in many database systems. I believe that DBP also uses it as well. There are multiple variants as well, right? Maybe TSO, maybe 2PL, maybe OCC, snapshot isolations. Keep the word snapshot out here again. But again, as I told you, I'm not going to get into a lot of details on MVCC, multi-version concurrency control, but just to let you know that 2PL and TSO, even though they are in use in some database management systems, but most of them now return to multi-version concurrency control. In summaries, concurrency is basically a two-edged sword. It gives you better opportunities to allow for to deal with the long-lived transactions, but you also need to handle it properly. Modern DBMS with MVCC and P1, we host a lab on present on March 10. As I told you, we're gonna have a quiz. So prepare for your mobile phones, scanning QR code, okay? So the quiz should be recorded. Let's not record a quiz. Or should we record a quiz? No, you don't want to.